morning, everybody. So welcome to WashU. So welcome to St. Louis. So I hope you had a nice travel and finding dorms, hotel, wherever you are located. Of course, if you had any, trouble issue, just send me emails so I can try to, solve and address if there are any issue during the day, during the week. I know some of you are staying in the dorms, so if you have any issue and problems, just reach out, okay? So people here are very efficient and are here to help. So today it is a pretty busy schedule, so I don't want to take too much time. I just want to point out in the schedule that we have 2 coffee breaks, one in the morning and one in the afternoon, and we have a lunch break, and we will all walk back to the physics building, okay? So it is a nice walk. We go there, we do the breaks, and then we come back here, okay? So I think we can start the band camp. So we have a technician in the room, so also if you have trouble with computers and connection, so we have some person to help. And yeah, so I think we can start. So thank you.
Hi everyone, my name is Özge. I'm an assistant professor at Miami University, and I'm part of band collaboration. So I will just start the band camp with a brief slides. It shouldn't take more than, I think, 1 minute. And then Moses is going to take the lead, and then we will start our hands-on exercise. And this is really to introduce our group, to introduce the people so that you know our faces. And then to have some, basic terms. Everyone should be on the same page before we start our hands-on exercise. So, Bandcamp is a part of Bandcamp collaborations tool, and so I will just start with introducing our team, and then I will briefly go over what band framework is, what we are trying to do, and then I will talk about 4 main modules briefly, but today you will be doing exercise on most of these modules. And we are working on these modules to provide tools to the community. So we are a multi-institutional and multidisciplinary group. So we have physicists and statisticians. And we are located mostly at Midwest. So first institution is Ohio University. So today, Daniel Odell and Alexandra Sempulski will be talking about their research and software tools. Second group is Ohio State University, and we have Viktor Stahl, Matt Protola, Dan Lianaj, and Joe Unity talking here and doing ISNET. And we have Michigan State University, Pablo Giuliani, Kyle Gabby. They will be talking today and doing ISNET as well. And we have Vitek Nazarevich talking about machine learning, doing ISNET, and today as well.
Mokyo has a poster.
Okay, Mokyo has a poster as well. Sorry, but not catching this. And we have Northwestern. Moses is going to take the lead. He will be doing most of the stuff, this first section. And I was a part of Northwestern as a PhD student and a postdoc later, and now I'm an assistant professor at Miami University. So, what is band framework? So our goal is to provide reliable predictions for inaccessible environments or unseen environments for physics problems, specifically nuclear physics problems. And in order to make sure that how reliable our predictions are, we do uncertainty quantification research. And our ultimate goal is to provide these research projects on uncertainty quantification using software tools. And what makes our group unique is that our tools provide an interface between physics problems and statistical solutions. I'm pretty sure you can just Google it and find many statistical tools or some physics problems. But what we are trying to make sure that we will provide an infrastructure that connects both physics problems and statistical tools. And our goal is to provide these tools to the community, so we're trying to produce well-documented, guided software products. And then the goal of the day is to introduce these products to you and to get feedback from you. And we have a nice website that you can Google and then find about us, our projects. So this is the first one, this is our website. And then we release our software packages and problems or examples, paper products, through an open source GitHub repository. So you can access that repository, download it, and then look our examples. And we always welcome feedback, so you can always, using GitHub repositories, actions and tools, you can always raise some issue, try to solve some problems that you realize. There can be bugs, as of course. And we are happy to communicate over GitHub repository or our Slack channel. So we released version 0.2 last summer, and we had surmise, which is a calibration and emulation statistical software, and Moses is going to be doing examples to introduce surmise. And we had Samba, which is a mixing package. Mixing is one of our modules, and Alexandros and Posti worked on that package, but as a group, today we're going to present a larger mixing package that connects many different mixing solutions. And we have some examples to illustrate how those packages can be used for realistic physics problems. And we are planning to release version 0.3 soon, and we have roles today. Pablo and Kyle will be presenting roles. It's different types of emulator. And mixing experts are going to be talking about their nice package, Tavaret. And Kyle is going to be talking about Bayesian Mass Explorer. That's a nice web-based tool that connects many different physics data sets with some uncertainty quantification tools. And we have Parmo, which is a multi-objective simulation-based optimization tool. We haven't connected Parmo with a physics problem yet, but as you can, throughout today you will see that when we do emulation and calibration, we can have multiple different objectives, depending on, if you want to build a, high predictive accuracy emulators, or depending on our calibration objectives, so we can construct multi-objective optimization problems. And we will be connecting Parmo with a physics example soon. And then Dianash is going to be talking about his simulator during ISNET. It's a nice stochastic simulator, and I'm pretty sure he'll be talking about the challenges and how he finds solutions for Bayesian calibration of his simulator. And again, we welcome any contributions to our framework, and we love collaboration, so feel free to reach out. So briefly, we have 4 main modules under BAND framework. So we have model emulation, model calibration, mixing, and experimental design. And we are trying to construct statistical tools for these main modules, and then we try to combine them with physics problems. And model emulation, today we will be talking about this a lot of times, but for those people who have not any experience, it's a predictive model that tries to estimate the simulation model's outcomes for unseen points. And most of the time people use Gaussian process emulators because they are flexible, and Moses is going to be showing nice examples regarding how we can use Gaussian process emulators. But it is not the only predictive model. there can be other types of emulators, and Pablo and Daniel will be talking about different emulators as well. Calibration. So we have this predictor model to understand simulation outcomes for unseen points. And calibration, when you receive observed data, say you conducted an experiment, you receive real data, it is trying to understand the best parameter setting that aligns this data set with simulation outcomes. And I think Moses is going to be talking about showing some small examples using surmise. And we have mixing, as the name suggests, mixing, we have many models, not one simulation model for a physics problem. Think about yourself, if you're a physicist, you might connect different groups, research groups, and each group can have their own simulator for the same problem. And the goal of mixing is to create one big predictor model that combines different physics simulators to have the best predictions. And our mixing experts will be talking about Tabaret and their solutions for model mixing methods. And we have experimental design. So here, experimental design can be grouped into two. So one group can focus on designing computer experiments, how to build globally accurate emulators, or how to better calibrate your computer models. So these could be different objectives, and then you design the computer experiment. So tomorrow I will be presenting my own research on that. But the second group is physical experimental design. How to design the physics experiments to increase the total utility of design. And this total utility, again, can be defined in many different ways. And I am also interested in that topic, and I do believe that our physicists are also interested in that, and Dick Fernstahl and Vitek Nazarevich will be talking, I think, through the end of the day more about this module. So I will briefly go over the module. Again, I'm not going to touch base on the details, just to be on the same page. I will be talking about these modules separately. So I have been saying simulators, right? So I'm trained as an industrial engineer, so we have simulation as a research area, and we call them as simulation models or simulators, and we use these models to understand the real-world processes. For example, during COVID-19, so I'm pretty sure everyone saw someone talking about COVID-19 on TV, right? They use epidemiologic simulation models to understand real-world process, because we can't really try every different changes to see how, for example, masking is affecting the cases, right? So we call them simulators, we call them computer models. Computer code, they mean the same thing. It's really a computer code, right? And now we have access to high-fidelity computer codes or simulators. So with an increasing complexity, of course, the time that takes a single simulation run becomes significant. So we need effective models, effective statistical solutions for predictions. And uncertainty quantification in one subfield in statistics, in order to understand how our predictions are reliable, and in order to make sure that whether we can trust our predictions using this simulation model. So for example, under band we have Fresco, we have many other examples, but I just use Fresco here to show. It's really a computer code written in Fortran. I am not the author. Philomena News, I'm not a physicist. Philomena News worked on that project significantly during her postdoc. It's written in Fortran, right? It's really a computer code for scattering experiments. And this is just an example of an input. It's like a TXT, right? You write the parameters, you define the reaction that you are running. And then you just execute it, because this is a code that can be installed like a package, right? This is why we call them packages. And then you can open your terminal and then execute using this input file, and it will produce an output, right? This is really, simulator is just a computer code that we can run. And typically, we say these computer models or computer code simulators have two types of inputs. Input X means controllable inputs, and then we have uncertain or unknown parameters that we will be using same notation. So this is one illustrating, we try to be consistent. And then the computer model takes these inputs and then returns the output. It's like a function, right? And if single run takes so much time, we need efficient techniques. And as I said at the beginning, typically Gaussian processes are the first tool that we try, because they are flexible and they provide uncertainties on our predictions. But our group, we have, for example, Bayesian trees that, as another solution. We can use Bayesian neural networks if we want to have uncertainty quantification. And how do we construct these models? They are really statistical models. We have machine learning. These are like data mining buzzwords right now. So for building these models, we need some training runs. So we create some input designs. We run the simulation using this design, obtain outputs. And using those runs, these sample of runs, we build these statistical models. And then we can use this predictive model to do predictions for unseen locations, right? We don't need to run. If you construct a really accurate predictive model, then you can just do your predictions at any input location. And calibration, typically in modern calibration, we use these emulators as an input to the calibration process. And by the way, we use emulator, we use kriging, what else we use?
Surrogate.
Surrogate we use, so those are the words that we use for emulators. So this is, I just wanted to show some pictures. So this is, I created this red line intentionally. It's like a bell curve, right? Normal distributional curve. So it is my computer model. So I created that function, and then, so these stars here are my training run. So I picked 3 locations. So this is really one-dimensional example that I want to show. So I did not include any controllable points, so X is eliminated. So I just use uncertain parameter theta as input to my function. And then I have run these 3 star locations as my training sample. And then, as you can see here, and I fit the Gaussian process. So if we just run at these 3 locations in the middle, the predictions are not doing good, right? The red line here is far away from the blue line, which is the prediction mean. And this shaded area is what we call uncertainty, so it's the variance. And then I have increased my number of sample. So here we have 5 points, and so right now I'm doing a better job here for prediction, right? Oops. And then 7 rounds, so it's better, right? Right now the true, at this point in the middle, the truth and the predictions look very similar. So today we will have, this is just a Gaussian process. Moses will be showing examples, and then we will be having different types of emulators and examples during the day. Calibration. So calibration, as I mentioned at the beginning, so we have input, computer model, output. Calibration requires some observed data. So you design the physical experiment, you run it, obtain the data set. And if you data, if you do some statistical tools, use them and find the best parameters. This is what we call calibration inference, and some people use inverse problem because using data we try to infer parameter values. So here, for the calibration problem, there could be different statistical assumptions. So one simple assumption is that, so here we have controllable design points x. So you did the experiment at these points and obtained the truth. And we assume that there is one correct theta value that aligns simulation output with the observed data with some noise. But there are, so this is one simple example on the assumption. There are discrepancies. We can say computer model is not enough to explain the truth. So you can assume that there is some discrepancy term between the computer model and the truth, so you can add up this. But right now, I think for today we're going to keep things simple and use this assumption. So Bayesian, so we're, as our name says, we are providing Bayesian tools. And in Bayesian statistics, we assume that the random, the parameters, those unknown parameters, can be represented as random variables. So using that assumption, we can say the posterior of the parameters, posterior density is proportional to the likelihood and the prior. So prior here is typically coming from the physics expert because they know the computer model and they can say these are the probable distributions for the input parameters or the ranges. And then depending on how we define our statistical model, we can construct our likelihood. So here I assume our errors are normal, so we can use normal distributions likelihood to construct them. And here the problem is that in order to compute the likelihood, we need to evaluate the simulation model at a given parameter value. So if this parameter, evaluating the computer model takes so much time, then we need emulators at this point, right? For any theta value, you can find the output. And my friends will be showing examples. So here I just wanted to show you one simple example again to have the terminology. What I did now, in addition to my first example that I have shown for the emulator here, right? I only had theta as input to my computer model. Right now what I did, now I included one controllable input variable x. So x really, the x-axis shows this x value, controllable input. And for different parameter values, I created a scenario where we have a computer model like that. And then we observe the truth. So these blue points here, I just created 5 points as my truth, y values. And by looking at this, right, for you, it shouldn't be difficult that at theta equals 0, the observed data are close to the simulation model, right? So you can say the best setting probably is around 0. And I use some sampling techniques to obtain the posterior rows. And as you can see, my posterior rows are around the true parameter setting that we can actually observe here. So here I am just passing this short. Surmise is one of our Python packages, and Moses is going to be showing this soon. And it has emulation and calibration capabilities. And again, our goal is not just to give existing methods, but our goal is to include techniques that we work as a research study. So, using surmise, for example, we have published some papers. So Moses' paper is new. It's published at Technometrics, and the method is included under surmise. And for example, then we'll be talking about his method, and here we use stochastic emulators and included that under surmise. And Pablo and his collaborators use surmise to get some calibration stuff done. And finally, I showed you Fresco eggs, so also we studied Bayesian calibration using Fresco as our physics simulator. So mixing, I am also, because we have great researchers here, so for mixing, as the name suggests, we access to many different simulation models. So here, again, I try to use the same model. So here, assume that we have these black dots as our truth, and there are two models. Just keep it simple. And all those models, I have calibrated them. So in mixing, the goal is using these black dots. How can we combine these two models to obtain one, great model, right? Superior model. And there could be different situations here. For example, this blue model is able to predict this region, this X value, but on the other hand, the red model is not able to do predictions, right? Some models are not defined at some input locations. Here, both of them are defined and they are doing good job, right? Both of them. But for at zero, blue model is better than the red line, right? So in this case, it's not really a combination problem, but you need to select the best one. So it is, it could be either finding these ways, how to combine these models, or how to select models at different input locations. And today, so we have some papers out, and John will be talking about his regression tree method, and Alexandra will be talking about her package, her model, and the solution that she found for her research. And then right now, these three great people are working on the cabaret package for mixing, and they will be talking about the package itself. And the last one is experimental design. Again, it could be computer experiment design or physical experiment design. For computer experiment design, we try to create this sample, computer experiment sample, in a way to maximize our utility from the computer experiment. So the goal could be to construct the best emulator that you can find, and you can have some limited computational hours, right? It is true. If one run takes a day, and if you have access to the clusters, and we have some limited budget, right? We need to be smart enough to get the utility out of this computer model and the physical experiment. So tomorrow I will be talking about the computer experiment design. Maybe next year we can talk about the physical experiment design of this myself. So this is an example of a computer experiment design and what I am trying to say. So again, this is a Gaussian process, right? I showed at the beginning. Here, my predictions are not looking nice, right? The blue line does not match with the red dashed line, which is the truth. If you have, let's say that you can only run four computer simulations, and you try to find the last point, right? You can generate your computer model here, or you can run your computer model here. But at this stage, you didn't run the simulation model yet. What you have is the emulator. So using this emulator, the goal is to find a design point to maximize the utility. So for example, if your goal is to increase the prediction accuracy, perhaps it will be wiser to select this point rather than that point, right? Because if you put here, these lines become closer to each other. So we will be talking during So tomorrow, myself and Dan will be talking. And we have, on Wednesday, we have Vitek Nazarevich talking about machine learning for nuclear physics problems. And Thursday is, we have many people. We have Dick Fernstahl, Pablo Giuliani, Daniel Odell talking about their research. And finally, on Friday, we have Kyle Gagby talking throughout ISNET. So feel free to talk and discuss our research projects. Thank you. Moses will take the stage.
Thank you, Özge. Hi, how are we doing? Great. So we are gonna switch gear. So did everybody get an email from Professor Daniel Phillips yesterday? So on that particular email, you'll find a list of links. Basically, today is the time that we go through, I think, all of the links, if not. So the first link would get you to a Google Colab page, and just so I make sure everybody tries, if you want to tag along. So how I designed today's session is basically I have a couple of talking points filling in some mathematical and technical details that Özge kindly left behind for this session to not be too boring. But I will primarily talk about Gaussian process. What we do is I will do a little bit of talking, and then let's have everybody code a little bit, use the package on Google Colab, and then go back to talking a little bit, and then see where we end up. And feel free to ask me any question during the time, like just throw me questions if anything is unclear. Two things I wanted to mention. One is I try to have this notebook as self-contained as possible, but also terminology-wise consistent with the other presentations that we have had so far. Well, which I'm lucky because I'm the first one. And yeah, that's the thing that I want to say. Before we start, I just want to get a feel of like where we all came from. If you consider yourself a physicist, can you raise your hand? Okay. Of course. Well, I'm not surprised. Just so you know, I'm not surprised, but it still overwhelms me. If you consider yourself as a statistician, would you raise your hand? Thank you, Pablo. Okay, we have a couple. You consider yourself as neither? Don't be shy. Oh, okay. Would you mind telling me, Jonathan?
Yeah.
Yeah.
I guess I'm a chemist.
Oh, great. Yeah. And, well, hopefully today's talk, some of them will be useful to you as well. Okay. All right. Great. So let's get started. Are we ready? All right. So
Can we just check that everybody
Yes.
can get to this page?
Yes.
Has anybody not gotten to that page? Oh,
Excellent.
You're all good.
So one thing that I want to say, if you got to my GitHub page, you can open it in Colab. So there was a little button on the top where you can open this notebook in Colab. And sorry, well, I keep adding things to what I want to say. If you hit save right now, Control S or whatever, it might show you that it cannot save unless you make a copy. So the best thing for you guys to do is to make a copy, save it for yourself, and this notebook is all for you to kind of go back and run different things and as a reference as well. We have about an hour and 10 minutes, which I think would be more than sufficient as we go through. So I will pause and take any questions if things don't make sense at any point. Okay. All right. So let's start with Gaussian process as an emulator. So Özge has introduce us to some of the terminologies. Just quickly talking about a simulator or simulation code. We call it F, and it takes in two kinds of inputs. In practically speaking, x and theta, the input and the parameter, don't make a difference to the simulation code. It's just an input. You basically need a combination of all the inputs and the parameters to be in the simulation model for it to give an output. That is what it is. We partition it into parameters and inputs so that we can understand one group better than the other. And we have, that is not what I wanted to do. There we go. So the key idea here with surmise, with Gaussian process being an emulator that is used for calibration, is the emulator should do two things. One is it should be able to predict. It should be able to predict at places that where you have not seen or not run a simulation code yet. And two, it should provide uncertainty around those predictions. So you should be able to tell how certain you are about those predictions. Well, a hidden point here, which Özge already alluded to, well, the emulator better be fast. If it is not faster than running the simulation code itself, then why bother? Like, just don't use an emulator, just use your simulation code right. And as well, this is a good time for me to ask, has anybody heard of a Gaussian process before? All of you guys have. If not everybody.
Ask the inverse.
Well, I don't want to pinpoint. But that is a great question, so that I know who to focus on. I'm kidding. Okay, so for who has used a Gaussian process before? Used in any way, like pull it up from scikit-learn or whatever. Okay, so heard of, used. Who has coded up your own Gaussian processes before? Okay, yeah, about the same people. Great. So at least at the end of today's session, you'll be able to, well, use a Gaussian process for sure. Okay. I'm not sure about coding one just yet, but that's okay. Let's get there. So quick terminologies about some setting and the data. What I mean by data here is the simulation output that I get. So today, what I will mainly talk about is kind of a deterministic simulator. Meaning that if you run it at a combination of an input and a parameter, you get the same output every single time. It's just expensive. But then we'll talk about a stochastic simulator in his talk tomorrow, and you will see that, well, sometimes when you run the same code, because of various reasons, you might get a different output, and that requires a different set of solution methods. So here I collected, for now, I'm saying that I have one fixed input, and then I collected n different outputs from n different parameters. And I just put them together into a column vector, call that a univariate case for our data. Then what it means by using a Gaussian process to model this is to say, this set of data would follow a normal distribution that is parameterized or categorized by two things. One, the mean function, and two, the covariance function. So the mean, you can choose a mean function and you can choose a covariance function. And at each of the parameter, you can evaluate it. That is what you need. And then what you're saying is, well, I assume that my output or my data follows this normal distribution. For any n, that is true. And that is what a Gaussian process is. Basically, you say, as long as I pick finitely many points, that will follow a normal distribution that is prescribed by this mean and covariance function. And once we do that, it's actually really easy to do prediction and uncertainty quantification because it is all baked into conditional distributions of the normal distribution. So, as we said, the emulator is basically a statistical model that can predict and give you uncertainty quantification. In this case, the emulator is basically the conditional quantity because it gives us a mean about wherever we want to predict that. So I call that mean mu hat at a certain theta. And then it also gives how variable that particular prediction is at that point, and I call it sigma square. Sigma square hat at the theta. Putting everything together, that is the goal of the emulator. One, prediction. Prediction, the mean can be computed with this particular equation, and then the variance likewise. Any question here? So this is just the definitions of how Gaussian processes are being used and the underlying equation. Okay, great. All right, let's look at an example. So you can run it with me. I'm running it kind of real time. Like you can run each cell at a time. What I've chosen is a kind of a classic example in calibration that we have seen using basic physics model, and it's a bar drop model. So imagine for a second this is very expensive to run. Well, it is not, but for today's purposes, sufficient. So it takes 4 different inputs. One is, hey, after you drop the ball, when are you going to measure the location? So that is the time. We call it t. And then where do you drop it? Like you could drop it at different heights, and that is the initial height is in h. K is the drag coefficient, and G is the gravitational constant. How, just setting this up with, I want to make sure I run these so I can run them later. Partitioning the same inputs into our x and theta space, like x is kind of something that we can control. So you can think of, if you want to run a physical experiment, let's say you get a ball of mass 1 kg, and then you want to know what the drag coefficient or what the gravitational constant is. Well, guess what? Go to different buildings, measure your height, choose your height, and then just drop it. And then hopefully you have a camera that you can like look at, hey, at what time, what location it is at, right? So that's kind of the simplest physical experiment that you can run. What you can do is, well, you keep choosing different heights that you drop. You observe at different times. Those are your choices. So we call them the input x. Yeah. The parameters would be the drag coefficient and the gravitational constant. You don't know about it, let's say, and that's why you're dropping the ball to find it.
You should just imagine you're on another planet. You don't know those things, and you have to do a separate mission every time you're going to drop the ball. So that's
there we
really
go.
expensive.
There we go, there we go. Well, that's the physical experiment that's expensive. The simulation code is still there. So, but yeah. Excellent. And guess what? That example will show up in a little bit. Okay, so far any question about parameterizing, just putting that into x and theta, and I've kind of put things into the same framework so you can just worry about x and theta. You don't have to worry about like the different inputs.
Can we just calibrate one more thing? who is not familiar with using Python? Okay. Oh, we are good.
Thank you. that would
This
be.
gets easier year by year. The first time it's like.
And I just want to comment, like from the first band camp to the second band camp to the third band camp, we did have kind of a growth. I don't know whether we can statistically like kind of like predict where the growth is gonna be or when it is gonna plateau, but that would be fun. Side project, student project, probably. Okay, so I did some quick just plotting. I'm pretty sure everybody has seen some sort of the results before, but let's look at what it looks like. Let's say I just grab a bunch of drag coefficients, a bunch of gravitational constant, and then drop the ball at 50 meters, I think. And then just measure it for 3 seconds. Let's say I can measure everything from 0 to 3 seconds, then this is what I get. Well, it makes sense, hopefully. Like, whenever the gravitational constant is pulling towards the ground, then this should happen. Right? When you have a gravitational constant that is like smaller, it drops less. If you have one that is larger, it drops more. Like, it's intuitive. And hopefully this is the goal for understanding emulation and calibration. So we need an intuitive model. One thing that I included here is to say, hey, let's put the drag coefficient between some range. So this is what Özge has kind of alluded to, is some kind of prior information, some kind of knowledge of the coefficients or knowledge of the parameter that you're dealing with. And with such knowledge, you can actually kind of restrict yourself to looking into those spaces. Otherwise, you can look into spaces where drag coefficients or the gravitational constants is negative, which, if k equals 0, then this won't run. Like, this simulator won't run, like, because it won't solve. If gravitational constant is negative, then you just fly away to I don't know where. So, maybe that is of interest, but this is out of the scope for now. Any question so far? Excellent. Okay. Because I'm building up about Gaussian process, I showed you a univariate Gaussian process, how we fit that. So univariate means that I only consider one output. So let's look at just at one input, meaning I drop at 50 meters every single time. I only observe its location at 2.5 seconds. Okay. So what I would get for all of the different you can see the figures as well. Then you can look at the location that you get from all of the different parameters that you tried. This is what you might see as your data. Does it, everybody okay so far? And I just want to know if you guys are running with me. Is everything running? Good. That is great. Okay, so now we have the data. Now we have the assumption that we're using Gaussian process. So let's go into surmise. This particular install takes maybe a little bit. Within a minute, I want to say. It is a pretty small package. But go ahead and run it because installation takes a little bit. But meanwhile, oh, it finished for me. Great. Because going forward, then I'm introducing how we use surmise, so I do want you guys to be ready and kind of get on to it. Who's hasn't installed yet? Oh, who has installed? Wow, that's great. Like from my experience, technology is never my friend, and today is a good day. Okay, so So the first thing that we want to use surmise for is emulation side of things. So, well, let's go ahead and import the emulator. So how we call it is from surmise.emulation import emulator. And how we use the emulator. I didn't show some of the structure. Now is a good place to go back. You can definitely run this, but at some point when you're coding yourself, you need to know what x and thetas are. So, actually, I can share this because this is interactive. I can just show you what is. Okay, so I told you that I'm just choosing one input point. So my x back is just 2.5 and 50. Like there's the time and the height. Notice that the shape of this guy is did it run? There we go. So I have one input with 2 dimensions. And every single time when you define an input, it will be of this kind. So you have however many inputs that you want, and then the dimension is fixed, is 2 in this case. Okay. And then similarly for theta, in this case, I'm trying out 48 different theta combinations, so G and K combination, and I get 48 out of them. So that is where x back and theta back are. Any question with that? Okay, great. So I think I want to be careful as well. F has to be, if I call my number of inputs m, and I call my number of parameters n, then f should be n by n. So now, if you go ahead and run the emulator, it shouldn't take more than a second. It should finish running. This is a flag that I always put in because for some reason we decided to ignore the warnings by default, which is not a great practice. Like, that would change, I believe. But for now, please include the warnings equal true, just because if anything is wrong, it can warn you. Okay, everybody built the emulators? I think I talked long enough for that to run. All right. Now, what I said is, well, we have created our emulator so we can predict. We can predict that, say, any parameter that we want. So how about just between the ranges of my k and between my ranges of the g, I create 30 points on the k space and then 50 evenly spread out points for the g space. And then, well, this mesh grid is basically just putting everything, every combination, and then into the form that I need it to be. So if you run this particular code and look at what theta vec test is, it should have 1,500 points. Okay. So we're predicting at 1,500 points, and let's see what happens with that. So what is might be slightly different from what we typically do is that the emulator, when you run emulator dot predict, so this is whatever you named it earlier, dot predict, and then you can give the same x vector, right? And then with the set of test parameters that you want to run. It returns a prediction object. And the reason is each prediction comes with the mean and also the variance, and also some other quantities that you might be interested in. So that's how we have designed it. It returns an object that you can call the mean and the variance. Does that make sense? Okay. So one little thing right now, currently surmise would take discrete number of inputs. And the prediction has to be at those inputs. But that can be extended, but right now we have to choose the inputs and stick to those inputs basically. Okay? Parameters, you can do a prediction everywhere. So if that has run, and I've provided a, so that we don't have to keep thinking about it plotting, and, oh, I already ran it. No, I wanted a surprise. There we go. So this, everybody got to this plot? Okay. Okay. This particular plot is the mean, just plotting the mean of the emulator. So using the data that we have, 48 points, we built an emulator. We are predicting at 1,500 points across this two-dimensional space. Remember what this is emulating. It is emulating the location after you drop the ball for 2.5 seconds when you drop it at 50, right? So at different, well, as we would know, like if you have a very low gravity, like all the way to this corner, then you have this very, like, drop very, very little. And then if you have almost no drag, a lot of gravity, then you basically just drop really quick. That makes sense, right? And you can see the contour plot as well is the same. One thing I want to point forward is, what if I actually go drop a ball at 50 meters and then measure it precisely at 2.5 seconds, and I find that it's 20. What does that tell? What does that tell us about the parameters? Ah, you didn't expect that I meant for it to be interactive. So I got a physical data point that says it is 20. What does it mean on this graph?
Well, it looks like you've got a range of parameters.
Exactly, but it rules out a lot of other ranges. So 20 is right here. If you draw a plane and then cut across this plane, you get a range of values of g and k that could give you the physical data point equals 20, right? But for all of the other combinations, you almost don't have to worry about them. That is what calibration is. Does that make sense? So by aligning this emulator with a physical data point, that shows you where I should look for those parameters. And in this case, well, it's still not 1 point, it's not one parameter, because you get, well, given we have one-dimensional data and we are predicting 2 parameters, that tells you that there is a range. You can only get so far. Correct? So that is the idea of calibration. Pointing forward, we would do that more sophisticated, wow, with more sophistication with surmise. But that is all to say, calibration is just a word for matching.
So if you calibrate at 2 points, is it the intersection of those planes?
Ah, that's a good question. So you would hope so, but not
Some
necessarily.
uncertainty.
Yeah, so the issue right now is, even if you have 2 points, when Özge mentioned about the data that you get, there's typically errors, right? And also, there will be uncertainty relating to how the emulator is also built. So you get a range of points, but you can squeeze your space towards those points. And in some ways, in physics problems, then typically what you would say is, well, the data is able to constrain some parameters, but not the other parameters. Because you'll use this later, I do want to quickly go through. So I plot also the uncertainty in with the same plotting function, just replacing the first bit with the variance instead of the mean. I use the standard deviation, it's a little easier to look at. You can see it is kind of squiggly, and it has a steeper slope on the sides, on the edge of the parameter space. And that is kind of a common issue that you would see with Gaussian process, because you don't see anything that's outside, right? Then your uncertainty is up. There are ways around that, but typically, hopefully, your true parameter really lies in the space rather than lies on an edge, because if you're on an edge, a lot of things go wrong. So you guys will be able to use this function later on in your own pieces as well. If you're interested, we can just look at, hey, if I change my drag coefficient or if I change my gravitational constant, and you can imagine each of these lines means in the k-graph, each of that line means a different gravitational constant, and then on the other, it means a different drag coefficient. So far, so good? So far, you don't have to type anything. All you have done is Control-Enter. Well, if you have not figured it out, Control-Enter. It's one of the shortcuts that you can do. So just quick recap. What have we achieved so far? We built an emulator. I let you know about calibration just a little bit by just visualizing what is going on. Well, that doesn't seem very helpful. Like I watched the ball drop. I know exactly where the locations are at different time points. So, well, let's do that. So we can drop it at different time points. We can drop it at different heights. And think about this. If you don't drop it at different heights, or if you don't observe it at different time points, you cannot nail down what the drag coefficient or the gravitational constant is. You might be able to narrow one of them. Okay, so now the first one is just generating inputs. I left that in for you guys because I feel like there's really no point of asking you guys to do basic Python. So right now, like I said, the inputs have to be discrete. So we have to choose the inputs. I have chosen 4 different time points, 0.1 second, 0.5, 1.4, 2.5 seconds. And then at different heights, I'm dropping the ball, 25 meters, 50 meters, and 100 meters. Again, mesh grid is just so that I can get all of them into a list, an array that has, how many is this? 3 times 4, so 12 different input with 2 dimensions. So after you run this particular case, then expect multi is what I call it, would be a 12 by 2 input. Is that correct? I'm hoping I'm correct. You can double check if I'm not. And what I want to leave you with, so one thing I didn't say is I am using the same parameter sets, the same 48 that I first collected data on to run this particular simulation and store everything in the cache. So right now we're doing multiple inputs. It means that for each parameter you would get 12 outputs, right? So each theta is corresponding to 12 of these runs, and it would have 12 outputs. And surprisingly, surmise can do multiple outputs as well. That was joking. Like we want it to be able to do multiple outputs, so we have surmise do multiple outputs. So for the following, I think I have little, yeah. So I put in a couple parentheses exercise there. That is for you guys to try. So you guys, I have given you the first one, and hopefully, well, some of the visualization, if you're not very fluid or very comfortable with the plotting, don't worry about it. We can go through them later. But in terms of using surmise, you should be able to use surmise already. You should also be able to do prediction. And I've given you the plot function for uncertainty and prediction. So you guys can play around, and we'll come back, I think, within 5 to 10, I'll check in. Or maybe you guys are already done. Like, that is also possible. So go through some of these exercises, check with your partners. Well, if you don't have one just yet, talk to your neighbors, build a team, and check. And I will check in 5 minutes, 10 minutes-ish. And I'll be here for questions. Any question for me before you test it? Excellent. Oh.
Stop working. Things working? Actually amazing that what's going wrong.
Right? I am very surprised so far. Often we have a very good setup. You look very confused.
Wonder, you're on the wrong tutorial.
By the way, I don't mean to put you guys in a code interview situation. Like, code this in half an hour, or code this in 5 minutes.
You just bring up ChatGPT and
Oh yeah,
code it.
and then, right. I wonder if ChatGPT
I
can
really
do
know about
surmise.
how old is it? I have ChatGPT 4, I can check. The first one wasn't old enough.
By 3.5. Haha. Yeah, it doesn't know surmise.
No, but it's that's the old one. So that's only 2019.
Oh,
I have
Ha.
I will check.
This was.
Yeah. What do we
I
get?
probably phrased the question wrong. I asked if you know surmise from the band collaboration. No available information on the band.
Well, we just have to build a band. All right, let's check in just a little bit. I heard less typing, so hopefully some of you guys have succeeded. Before going through anything, have you guys run into any error? Wow, it works? Wow, I am very good. So, okay, let's go through these exercises real quick. So just so you know, this is, well, just like 1/3 of what we need to do, right? Like this is just building an emulator and, okay. So what is the dimension of the output here? Wow, I really, it shows there. So 12 by 48, as I said, when you have a multiple inputs, meaning you have multiple outputs, then the dimension of this particular simulation output matrix that you should put into surmise should be the number of inputs times the number of parameters. If you try to do it, say you put the parameters on the rows and then you put the inputs on the columns, surmise would actually take it, but then would give you a warning, just say, hey, we tried to transpose your thing to make it match with your inputs and your parameters. So I can, anyways, okay. So if you only plot the data, I don't know whether, anybody plotted the data as well? Yeah, you get something similar? Yeah. Kind of. So the reason I only plotted against t, wow, this is, I'm very surprised. I'm a little, okay. That looks better. I like a labeled graph. Well, because the drop height, you can see it from the plots. So this is dropping from 100, 50, and then 25, and then with all of the different parameters, you get those observations, right? This is what you might expect. So right here, wow, okay, that's good enough. Did I leave this part in? I did not. Oh, no. Okay, great. So the default for surmise emulator is actually use PCG, something called the principal component Gaussian process, which I will talk about, but I just want you to know, hey, there's a way to do multiple outputs as well. So you would build it with the multiple x now, the same data as I said, and then your new F matrix. I explicitly called method equals PCGP, but it is the default as well. So once you run that, you might get a warning about some functions that's not found. And it is not necessary for building an emulator or do any calibration. So everybody got through the predict the output part at the.
That's where we stopped.
Oh, that is where we stopped. Great. Anybody got through this point just yet? Yeah, kind of.
I have no idea if I did it correctly.
Oh, okay. Oh, okay. Well, so the reason I left in one line of code, or there, I left in this particular line of code, right? The reason is, I told you that we have to emulate at the chosen inputs and predict at the chosen inputs. So this is one of the chosen inputs, 2.5 and 50. And I think that is the tenth. So remember that we have 12 inputs right now, right? And we actually built an emulator for all of them. We are only predicting at one of the inputs, and I have to tell you which one. And it would be good for me to do this real quick to let you see. So, if I look at the mean of the prediction, I get something like this. What does that correspond to? The row corresponds to the different inputs that I gave, and then the columns corresponded to all of the parameters that I tested at. I predicted at. Yeah. And why are there 1,500? Because I have 30 of the K's, 50 of the G's. So I think with index 10 is where my 2.550 lies in. So I basically pick out that particular input, the output corresponding to that particular input, and also the variance. Does that make sense? Kind of. Should I repeat? Should I clarify?
Can you repeat this?
Okay, great. So what happens is we predicted at 12 different places, yeah, with the different inputs. And the emulator currently you would have to predict at all of those 12 inputs, and then with whatever parameters that you give it. Okay? So that is what this prediction object gave you. It predicts that all of the 12 outputs and the 1,500 parameters that we wanted to test. The reason that I pick out the one row with 1,500 outputs is that is the particular row that corresponded to my input 2.550. Does that make sense? What's your name, by the way?
Kevin.
Kevin. Thank you. Thank you, Kevin. Okay, so if you get so far, which you also have to answer correctly, we can visualize once more just what the what the prediction and the uncertainty looks like. It looks very similar. Like we don't expect it to change any much, right? Because it basically consists of the same data from the simulation. This it's just that I emulate at more inputs at one time. So, for example, if I happen to change my let's change it to 0, which is the first input, then you will see something that's different because it has not moved quite yet, right? It's 0.0 seconds and then with almost no drag. So this is what you get from here. Oh, sorry. Wait, what? No, maybe I shouldn't do things on the fly. That's the usual lesson here. But I think I have an explanation. Okay, let me get back to this a little bit more informative one. So, kind of the same thing happens with the uncertainty. The predictive variance typically goes up when you hit the boundaries of your parameters. And that is just by using a GP, that is what you get. Unless you specifically give like further restriction to a GP, you would have this phenomenon. So whenever you see something that is kind of blowing up, especially with your prediction uncertainty, check where you have data and check what your space. What? Okay. Any question so far? Seems easy to work with. Like everybody, did everybody build an emulator from just now? Basically? Okay, great. Okay, I do want to just say a word about principal component Gaussian process. It is not the only way of doing multiple outputs. This is one way of doing multiple outputs. Simulator, it is primarily designed for efficiency, but it surprisingly works very, very well. And what it means is, well, right now, for each parameter, like I said, you have m outputs. And for simplicity's sake, I say that each m outputs is created by each one input. Yeah. So one input produces one output for each parameter. I put them all together into a vector, and I call that bolded f. What principal component Gaussian process is trying to do is to say, hey, we can find some sort of transformation matrix that is kind of a rectangle, so you have more rows than columns, meaning I can model m outputs with only k Gaussian process, kappa Gaussian process. So the bolded g of theta is what we actually throw into a Gaussian process, but we need less number than m to model them. So in the simple case, you can imagine, hey, if I have multiple outputs, why don't I just emulate all of each output individually, which you can, if m is not too long. Yeah? But once you increase m, so say currently we have 12 inputs, some examples would involve like 100 inputs or 200 inputs, meaning then for each of the input, you're creating one Gaussian process. Well, I only gave you what? N equals 48. So 48 parameters only. 48 is easy because you're inverting 48 by 48 matrix in the creation of the Gaussian process. But when you're thinking of your number of data points being, say, 500 or 1,000, when you get higher, the creation of this emulator takes n cubed times, so it scales with n cubed, and whenever you have more data points, it's pretty costly. So in light of that, the principal component Gaussian process is trying to do a kind of projection onto a smaller space, and then only run Gaussian process on that smaller space, and then you project it back up. That's exactly what this is, and people typically assume that each of the Gaussian process inside the G is independent. So you can just model each of the G's alone. I told you about this matrix already. Right now we get a new emulator, an emulator that gives you multiple outputs and gives you, well, at each parameter a covariance matrix instead of just a variance system, right? Because we now have multiple outputs at each parameter. The form of it is basically the same as before. So in the past, we have the mu hats for each of the GP, correct? Right now, well, we still predict with all of the GPs at the new theta, but then you just project it back out to the m dimensions. Yeah. And similarly, just linear algebra would, can give you the covariance matrix at a certain parameter for the original multiple. I lost half of them, did I? Any question at this point?
I guess what warrants this projection that we're doing? Like, what does that imply about the data?
That's a very good question. So what it does is it relies on the correlation between your outputs. So principal component or principal component analysis, if you guys have run into it in, say, machine learning or statistics, is relying on each of either the column or the rows. In this case, is across the outputs that you have some correlation. Then you can project without losing much of the data. Imagine if all of your outputs are actually independent, then you actually need all of them.
Okay.
That makes sense? So that is relying on the correlation on the output, we are able to reduce the computational cost by considering just a smaller dimensional data, if that makes sense. Yeah. Okay. Well, that was half of it, right? We haven't gotten to calibration just yet. Let me check the time. I have 18 minutes. Oh, no. Yeah, something like that. Okay, calibration. So right now, we are doing calibration in the multiple output case, meaning that I can observe some physical data at all of the inputs that I prescribe, and we think that it should line up with some particular parameter with some error. And in this case, the error has to be multidimensional, because right now we have, so it is a covariance. As Özge has brought us through the Bayesian part of it, then we are going to find what the posterior is. That is basically what calibration is like. And you guys already thought about this, and you guys are exactly right. It basically constrains your parameter space based on the data, physical data that you have seen. And that's the thought experiment that we've done earlier, and why that gives you just kind of a band of parameter values. Okay. For the sake of time, because I want you guys to get to calibration, you can look at what the likelihood looks like. This is basically just a multivariate normal distribution. And if you use an emulator, you integrate out the data that you get from the simulation, and then you get to a similar form as well. Okay, now the exciting story. So we actually were handed some data from someone, like from the outer space or whatever. Like you name it, just some different planet. And they basically run exactly the same experiments. Went to different heights, dropped different balls of, well, surprisingly 1 kg mass. So you think that your simulation model will work for this case. They have told you, hey, this is the experiment that we've run, and we recorded basically what the values that we observed with, well, just variance of 1. So it's like, and we think it's not that bad. That's the best that we can do. So this is the physical data that we've gotten. I've built for you guys the new set of inputs, right? So so what you can do here is, if you don't want to choose your new set of parameters and go through just building the entire parameter sets, you can continue to use theta back. That would be sufficient. That would be 48 data points. And you can run exactly the emulator again. By the way, a way to cheat is if you go to my GitHub, you will find the filled-in version, and we can also see every bit of it. So now I'm creating my new emulator at the new input. What is this is the same things, the predictions. So I'm gonna fast forward. Okay, coming to calibration. Sorry, I know some of you guys are trying to catch up. That's why I give the cheating tip. So we need a prior. So we know what the likelihood is. We haven't gotten the prior yet. So what I earlier suggested is k lives in 0.001 to 0.5, and then g lives in 5 to 40, something like that. To do calibration in surmise, we have to define the prior. What defining the prior means is to build a class, whatever name you call it, and we define two functions. The first function is the log density for the prior, and the second function is you have to be able to sample from that density. Any question with this? Just generate random variables that correspond to that particular density. For this particular case, I used a beta, a scaled beta distribution, and I will show you what it looks like. It looks like this. Yes?
There's a question.
Oh, yeah. All right.
So, how sensitive is it to choosing a different distribution? Suppose I wanted to choose something else.
That is a very good question. So let me show just the example here, and then I'll. So in this case, I claim I don't know much, but I do know that the parameters kind of live more likely inside the space rather than by the boundaries. So you see that I created something that's kind of bell curve. So it could be informed by physics. Bell curves are nice because it gives you a strict boundary, kind of. If you don't want, so for an application scenario, some parameters may not even return an output because it's undefined at some place, or some solution code within the simulation code wouldn't return anything or wouldn't converge. So in that case, having some reasonable boundary, you can define it in the prior. What in the Bayesian calibration setting, you do want to either try a bunch of different priors, like you can do a kind of the other way around a Jeffreys prior, which is like kind of a U shape. Just make sure you're covering the entire space, and then sometimes people do a uniform to say, hey, I really know nothing about it. But the fact is, whenever you choose a prior, you have chosen something. Okay? So it is really a choice. But if you change that prior by a little bit and your prediction changes drastically, then that choice probably has some problems, right? Your emulator or your calibration should be robust to what you choose as a prior. So because we have two parameters, I also built a plot function for the kind of, hey, can I plot a 2D histogram is what they call it, this. So the darker it is, the more density there is, and then the lighter it is, there's less density. And in this case, it's kind of like a blob because of this particular shape. But this is the prior. So it kind of covers the space. So meaning, hey, all of these potentially good parameters search for it. Okay. So coming to calibration, we then import the calibrator, and we run it as follows. Like, it doesn't look very different in a way. So you need an emulator in this case, and you need your physical data, which is Y. Well, we need the inputs, we need the prior. The methods and the arguments here can be changed, and that I will come to that a little bit later. These are just specific names for different type of calibrating methods and different centers. And what you also need is a variance of your physical experiments. So if you think about that, it corresponds to your error that you have in your physical experiment. So if I calibrate this, so calibration typically takes a little longer because of the Markov chain Monte Carlo that is running underneath. So MCMC, oh, it finishes. So MCMC is basically running sequential chains. Hey, keep drawing and see whether this parameter is good. Throw away if it's not, keep it as if it's good, and then keep going. And then eventually it reaches to something that looks like the posterior. And in this particular case, I could draw from the calibrator by calling the calibrator name .theta, which is getting to my parameters, and then it has an associated random number generator as well. So if we, oh, did I not work? Oh, because I changed. Yep. Because if I don't think I changed it on yours, so you don't have to worry about that. But if I did, I'm sorry. So this might be what you see is the first row is drawing from the drag coefficients, K, and then the second row is drawing from the gravitational constant. And this might be what you see as a chain, so-called, like MCMC chains or parameter chains. This is the trajectory that your sampler has gone through, and then it retains all of these samples. What it happens is, by the end, it should kind of converge to the posterior distribution. So what we have here is, given the data, we think that K is more likely to look like this, and then G is more likely to look like here. Does that make sense with calibration? So one thing that is probably good for us to check is whether it makes sense. And checking for correlations in the posterior is actually a very good way of looking at, well, whether those parameters should correlate. And in this case, we see a negative correlation. Well, that kind of makes sense, right? If for the same set of data, if the drag coefficient is smaller, then it means that the gravitational force is larger to see the same set of data, and then vice versa. That's exactly the intuition that we've come to when I said, hey, cut across that plane, and you get a band. And that is exactly what you get from here. Just that this is through proper calibration. Any question? Great. Oh, all right.
Well, I was just kind of curious. So, suppose this planet had new physics. What would happen to the posteriors here if we tried to do this calibration?
What does it mean by, sorry, you have to educate me. What does it mean by new physics?
So suppose our model isn't good, and there's something
good
else
question.
going on. Would we be able to see that our model is good?
That is a great question. So one thing you would see is in the prediction, well, you predicted some values, but then you might arrive at a wrong parameter because it has to kind of compensate for what you didn't do in your model. That's why where Özge presented as saying, hey, there can be a discrepancy term that we can also model to account for what if my simulator is away from my physical system by a kind of consistent or systematic effect. Great question. And then from the calibrator, you can also predict. So at first we just draw the posterior samples. Here you can also predict, and this is kind of what the calibrator is giving you. It looks at the blue crosses, which are the data itself, and then these are the predictions, the calibrated emulator. One thing I really want to show, because this is kind of, well, this is my work. So finally, we have four minutes for me to tell you what I've done in the past year. But as I alluded to earlier, simulation codes can fail. Like, it can fail for many, many different reasons. One is if you throw a simulation code into a cluster, if one of the computational nodes fails, then you might not get something back. But that is recoverable because you can rerun the simulation. But sometimes your simulation code relies on, say, an iterative solution method, like you're kind of converging to your answer, and it doesn't converge because your input is no good. If that is the case, what do? What happens is I build a pseudo failure system. The same set of inputs that I'm considering with what is given by the alien guy, and the same set of parameters that and what I say is basically if you have a too small a drag coefficient or too big of a gravity, the simulation code crashes. Okay. Then you see something like this. Well, what do you do then? Well, you could arguably just take out all the columns with the process. You have 70% of your data left, kind of. Well, nobody loves to throw away data, especially when they should be meaningful, right? Them failing actually tells you something. And the remaining, well, this one does not. This one is random, like based on just something. But based on where you see a value, it might be informative for your calibration. In this case, building PCGP, the principal component Gaussian process, is a little tricky. Well, I put it in there. It doesn't hurt to try. But it should crash. The reason it crashes is it is trying to grab the correlation between all the outputs, and then a lot of not values are in there, cannot solve for it, cannot decompose a covariance matrix, it crashes. I said that, hey, you can model kind of each column, each location or input independently. That's fine, but that is when the size of the data is pretty small. But you can imagine when your size of the input grows, as your size of the parameters that you collected from grows, then this is not very viable. Okay? And throwing out the data is, hopefully we don't have to do that. You add two characters to the surmise code, and it fixes all of your problems. Well, okay. So there is a method that we have developed as part of the band called PCGPWM. Is retaining the good things that we see in principal component Gaussian process, but it deals with the missing data without throwing out anything. I won't. If you're interested, you can ask me about it, but I won't go into the details because I know everybody is dying for coffee right now, after this hour. I left some of the empty slots for you guys, and as you can imagine, it takes a little bit longer. I did the same thing again, did I? Oh, if you give me, okay, so this is what you get from using a new emulator that deals with missing. So this is doable. So if you think about any physics application that looks something like this, you can give it a try. So that is how you emulate with surmise and calibrate with surmise. Two final notes that I want to give. And yes, so forgive me stealing 2 minutes of your coffee time. This is surmise, and if you look into surmise, and it basically has a bunch of folders that contains method. And if you remember how we call the surmise emulator and calibrator, we basically say which name we're calling the method. Meaning you can mix and match an emulator and calibrator methods. And what we have done is we called PCGP, we called PCGPWM. What it also means is I don't love any of your methods I'm coding up my own. Just push it into this directory, the code. For an emulator, you can run the calibrator with that emulator. As long as it gives the prediction and it gives the uncertainty. So that is where the surmise emulation calibration kind of modular design is supposed to be for you guys to, if I want to code up an emulator or I want to code up a calibrator, you can just add it in and mix with the other things that you see. And that is a way that we encourage contributions as well. Oh, I did not ask the question, but this is the answer for treating missing values. If you want to see more of the details, you read the paper and you can ask me any question that you have. Okay, I won't continue to steal your time. Thank you so much. If you have any questions, I'll be around for the day and tomorrow.